All right, good morning, everybody. So I wanted to do a quick video here just showing how you can use ImageJ to quickly review your MPAD data, help you visualize it. Um, just some limited processing you can do with it as well. Um, and then how to actually export it so you can then process the data later using whatever program you're using, to reconstruct your STEM images or do whatever it is you're doing with the data. Um, Whether that's like I have MATLAB scripts for this. I know there's a program Pi 4D-STEM, right? Um, and I'm not sure how that works, but generally speaking, I believe you actually have to export the individual diffraction patterns to do that. So I'm going to show you how to do that with ImageJ as well. So let's start here. We'll go to File, Import Raw. So if you saw the video on use of the MPAD, um, you saw that the file outputs, right, either for the scanned, the 4D STEM data or the series data are in .raw format. So if we start by, um, so actually let's start by looking at a series data. So this was a series that I took of a DP from the gold palladium sample, and this was with a parallel beam. So I use this actually for calibrating the camera length. So yes, you can collect parallel beam patterns with the MPAD if you want. That's not usually what it's used for, but again, the reason I used it was for camera length calibration. So let's actually talk about um, how to to visualize that data. So again, we find it. This is the .raw here. You can right click. It's going to say series X1000, and then it'll be .raw. It's not showing the extension. You can go ahead and click open. And then your image type, you want to be 32-bit real. The width is 128 by 128. That's the pixel dimensions of the diffraction pattern. And then your number of images. So this is 1,000 in the series. So we're going to put 1,000. And then you want to do 1024 bytes as your gap between images. So then you want to check little endian byte order, and then virtual stack. So the way virtual stack works is if it's a virtual stack, it doesn't actually load all of these images in at once to ImageJ. It only loads in the one that you're looking at in the stack at a given instant. And so this helps to reduce your use of memory. Um, it does limit you in terms of what you can do as far as processing the data if you use a virtual stack, and it also can be a little bit slower with looking through the data, although considering the size of the individual diffraction patterns, it's really not an issue in terms of speed, but it's an issue in terms of like trying to process all the data. So, but since we only have 1,000 here, which is a small data set as far as MPAD data is concerned, we don't need to use a virtual stack. When we open up an actual 4D STEM scan, then we can use this. So, all right, so we'll just click OK. Okay, so then here is I'm holding down Control and then scrolling with the mouse. Whoops, what did I do? Okay, and then scrolling with the mouse wheel. And then if you want to you can right click and then original scale to put it back quickly. Come on. Why is it not doing this? Come on, please. Okay. Original scale. There we go. Okay, so when you import this, so again, this is a series. So you can see as I scroll through here, it's kind of hard to see the dynamic range even with the beam. So the direct beam is blocked off. The dynamic range is still quite high. So it's a little tough to see these. So one thing we can do here is apply a lookup table, and then it becomes a little bit easier. You can see there's a shot noise as we go through here because these were, just 1 millisecond exposure. But one thing we can do, because they're all the same pattern basically, right, is we can compute the average pattern, okay? So if you select the series and then go to image stacks and then Z project, and so we're going to do the start slice as 1 and the stop is 1,000, and then we're going to do average. And then if we do lookup table, you can see that has smoothed out the shot noise rather nicely. And then if we do image adjust, brightness contrast, so it's showing, it's plotting the absolute contrast limits as black and white here. So these are the max and the minimum in the image. So you can have it do auto, but because this is kind of a weird histogram, it might not. Yeah, so it helped a little bit. And then if we bring down the maximum, see, it's hard to see everything else without. It's actually not too bad right there, believe it or not. But this is still a little bit harder to see these outer rings here. So again, that's by manually adjusting the contrast limits. So let's just assume this is the best we can get with just keeping the image as is, right, as a linear scale without right, by just adjusting the contrast limits. So let me go ahead and I'm going to duplicate this. Duplicate. I'm going to call this gamma. And then if I select this and do reset, it will put it back to the original limits. And then I'm going to do another one. I'm going to call it log. And same thing. Okay, so now with the gamma correction, go to process math and then gamma. And if you make this value less than 1, it's going to make it easier to see the lower intensity features. This was a mistake I made in a previous video. You don't want it to be greater than 1, or it's actually going to increase your dynamic range by making gamma less than 1. It actually decreases the dynamic range and it makes the lower intensity features easier to see. So if you click preview, so now it's going to go black like this because you need to readjust your contrast limits for the image. Okay, so you can click OK. And then if we find brightness and contrast, click reset. Okay, so you can see now the dynamic range of the image is a lot smaller than it was for the linear scale. Okay, and this is without doing any auto adjustment. So if we do auto, you can see that boosted it a little bit more. Again, it's, with these high dynamic range images like this, doing the auto adjustment is a little bit tricky and doesn't tend to work quite as well. So you have to kind of use your judgment there. But this is, I think, an improvement over what we had as far as the linear scale is concerned. And let's just put these on grayscale just to kind of make it a little more, right? Because your eye, I mean, you typically use grayscale with this. So yeah, you can see definitely. Now if we bring down the maximum a little bit more, that's brightness, sorry. Let me click reset, auto, bring down the max. Yeah, so there we go. And then if I find the log, let's put this to gray. And then you want to do process, math, and then log. And so the only stipulation with calculating log is that all of your pixels has to be greater than 0. Okay, so you can't have 0 or negative values or it will bark at you, I believe. But then we'll go to image adjust brightness contrast and then do reset. Okay, so you can see this decreased my contrast limits my dynamic range even more, right? So now we're only going, from 5.5 to 13.33, okay? So we don't even really need to do an auto adjustment here, but we could if we wanted to, right? And that probably helped us out a little bit more. So yeah, usually with images like this where you have like good signal to noise, doing the log with the DP, I should say, with DPs like this with high signal to noise, doing the um, the log version is probably optimal here. So, and again, these are for a parallel beam pattern. So we can talk about now with the if we're taking like a seabed, which is what we're usually doing when we collect DPs with the MPAD. Okay, so let me go ahead and close these. And again, if you wanted to save these, now if you want to keep the contrast limits here, what you have to do is click Set. You want to click Set before you save it, and then click OK. And then if you save this image, so you can just do Control S. And I believe if you save it as a Series X1000 log, adjust, we'll do auto. And if you put it as .tiff, I believe it will automatically save it as a .tiff or as a TIFF. So click Save here. And then let's make sure here. So if we actually open this back up, open. Yes, so it kept the contrast limits, but that's what you have to do if you want to, save the tips here. Okay. All right. So let me go ahead and close all these. Let's not save this. And let's talk about something a little more interesting. So we'll now import an actual 4D-STEM data set. So this is the one I imported or I created in the tutorial for collecting the data with the MPAD. Okay, so now your number of images is going to be 256 by 128, which is the scan dimensions. So if we do 256 by 128, we get 32,768. So we're going to do 32,768. And now in this case, just initially anyway, like this is getting a lot larger. So the data set now is going to be over 2 gigabytes. Each pattern itself is only 65 kilobytes, but then when you have 33,000 almost of them, that adds up quickly, and you have gigabyte range. So you can use a virtual stack here to make this easier. And then if we wanted to visualize it, we may need to create an actual stack, but we'll leave this now because it's only going to take up just enough memory, right, to read one pattern at a time. So we'll do virtual stack. Okay. So if you wanted to open this up as a stack, you need to have enough memory available for the whole data set. And so you have to allocate that in ImageJ. So if you go to make sure, if you go to ImageJ, edit, options, memory and threads. And so for your maximum memory, you could put like whatever your RAM is here. So I have 8 gigs of RAM on this. Now for the parallel threads, if you open up your task manager and click on performance, where you have logical processors here, that's the number you want to put there. So you can see I have 8 logical processors, so I have 8 for parallel threads. Okay. Okay. So now, with this, since each image is now different, right? This isn't just a series of the same image, which only has a variation of shot noise. If we do image type, or sorry, image adjust brightness contrast. So if we do if we click reset here, so this is for the first, these are the limits for the first image here, but it's applying these for each other image as I scroll through here, okay? So if I click reset again, it's going to readjust these for whichever image I'm on and apply that to each image in the stack, okay? If that makes any sense. So this is a little bit tricky, right? Because obviously what's in each DP is going to be different, right? So this may not, work very effectively. But the other thing too, of course, is, it's tough to actually visualize this anyway on a linear scale, right? So if we just copy, let me see here, if we bring this down to maybe see a little bit more. Okay, so okay, now let's just copy this one. So if you just want to copy one slice, you can go to image duplicate and then just don't check duplicate stack. And then reset. And then let's just mess with this one. So again, I'm going to do duplicate. Rename. And then I'm going to do duplicates again, and we'll call it log. Okay, process math, gamma. See, the preview doesn't really help us here, but just click OK, and then reset, and then auto. And that's an improvement, certainly, over what we were getting with the linear scale, which is the auto adjustment. So still a fairly high dynamic range situation here. So let's go ahead here and let's do the log calculation, process math, log. Okay, so now because the individual patterns are noisy, right, you can see that when we do log here, this is also going to be kind of noisy. I think actually with this, if I go back here to the original data, it's actually claiming there were negative values here. So that's interesting. I don't know what it did. I think it might have like truncated or brought these up because you're not supposed to be able to obviously take a log of a negative value. So I'm not sure what it did there. So, but it had some way to deal with the numbers apparently. So, anyways, be that as it may, this is what your individual seabed patterns are going to look like because it's like I said, it's very noisy there. But that's easier to visualize as far as what we were seeing here with just the one. So now the question, of course, is if we want to do this to each pattern in the stack, what do we need to do? So let me go ahead and close these. Now, one thing we can do here is we can do an average for just a few frames within like the vicinity. So let's say, so you're at slice 116,882. So if we can do a Z project here, just do stacks, Z project. So let's do 1685, 16885. And let's go to 16895. So we're averaging 11 frames. And let's see, how this improves here. So we'll do analyze, sorry, process, math, log. Okay, so that definitely improved things by doing that. So yes. Okay, so that was averaging 10 frames. Now, of course, right, because our beam is moving, this is not the this is averaging over different positions and different DPs, but that does help to smooth out the shot noise. Okay. Notice, right, I didn't do log of the stack first and then do the average. That's not going to work. You want to keep the stack without having done any math to it before then. Okay, so these are still just on a linear scale in the stack. You want to make sure to sum them first and then do log or gamma, or average them, I should say, and then do log or gamma rather than the reverse. Okay, but then let me go ahead and close this. All right, so if we want to do this to every image in the stack, so if we try to do this now with the virtual stack, so if we go to process, math, log, and say, do we want to process all images? See, the problem is it doesn't do this with a virtual stack. So what we have to do is we have to duplicate this to a real stack. So we have enough memory for this. It's asking us, we're going to need that much, which we have. We've allotted that much. So we can go to File, sorry, Image, Duplicate, and then we're going to duplicate stack and click OK. It's going to take a little while here. Now, unless you have like enough RAM, I don't think, you have to have it's at least 17 gig if you wanted to open up the full data set, right, in a complete stack. Okay, so now we've got an actual stack, and now we can do process, math, log, and then yes. Okay, and now we can play this through, and we can actually, so now again, if I click reset, it's going to adjust this based on each, whatever DP it's on. Okay, and if I do auto, same thing. Now it's going to apply these contrast limits to every DP in the stack. Okay, but you can see that's way easier to visualize now as opposed to this guy here. Because again, we put this on a log scale. Okay, again, this is just for visualization, right? When you're actually calculating your STEM images, you don't want to convert them to log and then do the calculations. Right? You want to leave them on the as collected in the as collected values for the intensity. Okay. And actually, just for fun here, now I think actually with Zoom it may not be showing this as fast as I'm seeing it right now, so I apologize for that. Yeah, if you add a lookup table here, then neat. We'll do grays, and we'll do grays here. And let me stop this. Let me stop this. Okay, so one thing I mentioned in the data collection video is how these DPs, they're flipped upside down relative to how they should be oriented when they're collected by the MPAD. Okay, so to adjust that, we can do that quickly in ImageJ. So again, select your stack. And of course, you could also do this with your post-processing software as well. It's an easy manipulation, but if you go image, transform, and then flip vertically, yes. So that took care of it. Okay. And now this has the proper orientation relative to the actual image itself. Okay. So that's something to keep in mind, right? If you're trying to, relate a DP to the image, you need to have proper orientation. So you need to make sure to do that, or you might get some confusing results. Okay. And then one thing we can do here, so I showed you how we can do position averaged DP from, part of the stack. Obviously, we can do that for the whole stack. And just I'll prove it to you, right, how this only works by doing the average for the as received or the as imported patterns rather than doing it for the log versions or after you've done the log calculation. So if I do image stacks, Z project, it will do the full stack and we'll do average. And once we have it, I will convert it, then do the log calculation, and then it will be easier to see. Or again, you can use the gamma. I think the log works a little bit better. Okay, let me duplicate this. Oops, no, I don't want to crop. Okay, math, log. Shortcut for brightness contrast is Control-Shift-C. Okay, and we see a nice characteristic, and that's just with the setting the contrast limits to the absolute minimum and maximum. Okay, if we do auto, come on. Oops. Okay, so it didn't. This is weird how if you do auto multiple times, like it actually will readjust it. So sometimes you have to kind of use your discretion here. That looks better though than what we were getting just by the full limits, but the full limit still looks pretty good here. So, and we see a nice characteristic polycrystal and diffraction pattern that we would get if we, formed position average seabed with a small semi-angle of convergence. In this case, it was about 1 millirad. Okay. All right. So then to prove that you have to average the frames and then do log, let me show you what happens if you try to do it the other way. So we did log to each of the patterns, and then we're going to do the average. So if we do image stacks, Z project. Okay, so you can see, right, because now this was an actual stack, and then what I did with the with this one, I did this from a virtual stack. So you can see, right, the math went really fast because the images were already all imported with a real stack as opposed to a virtual one, okay? But let's see here. Do this. Okay, so you can see here, there's not a lot happening here, again, because, yeah, so that's why this doesn't work, okay? There's just your mathematical proof, right? So again, or your visual proof, okay? Keep the images as is without any math, then do your averaging. Then if you want to apply log or gamma, you can do that, okay? All right. So we'll go ahead and close this. I'm going to go ahead and save this one. So we'll do Control S, and I'm going to call this log adjust.tiff. Okay. Your other option, of course, is you can go to save as and save it as, but I think if you just do it that way, it does the same thing. But let me go ahead and see if that happens. So if we close this, let's make sure they are the same. Open. Okay. That was the one we saved directly. And this was the one we saved by going to the menu. So yes, they're exactly the same. So Again, about 65 kilobytes each. Okay, so that's just a quicker way to do it. Again, if you want to use like JPEG, I think you can just do save and then put the JPEG extension as well. All right, so last thing to touch on here is actually exporting the DPs to whichever program you're going to use for your reconstruct your data. Okay, so one thing to keep in mind now, again, we don't want to export the ones that we've done log calculation to. Okay, you don't want to do that. So we'll click no. Okay, so with this, we applied changes to the, but as long as we don't click set here, it's not going to actually apply this when we export the data. Okay, so it's actually like if you do that, like if we clicked set here, I'm not going to do this, but then it'll actually apply these contrast limits to every image, and that will actually change the pixel values or some of the pixel values, and you don't want to do that. Okay, so make sure you don't. If you did a digital adjustment here to the as received stack, make sure you don't click set here. If you can click reset here, and again, it's only resetting for this image, but again, as long as you don't click set here, when we export these, it will not modify the actual pixel values for any of the DPs. Okay, so you don't need to actually import a full stack to do this, which is nice. Again, because if you did a full 512 by 512 scan, that will take like 17 gigabytes of memory to have a full stack. Okay, so you can use a virtual stack for this. One thing to keep in mind though is before you do the exporting, you definitely want to, unless you can do this with whatever software you're going to use to analyze the data, you want to make sure to flip vertically. Okay, so you have proper orientation. Okay, now I think if we do this, is it going to make us do this? Okay, so now here's the problem. So yes, so unless we convert this to an actual stack, now 2 gigabytes is not a problem, but I don't have enough RAM to open up the full stack, or the full date, like for a full 512 by 512 scan. I don't have enough RAM to do that. So basically, unless your scan is enough to be opened in full, the easier thing to do is probably to just flip the images vertically with whatever software you use for your reconstruction. Okay, but you have to keep that in mind that you need to do that. Okay, when you actually do your reconstruction, right? You gotta flip your DPs about the horizontal axis here, which they call flipping vertically. Okay. All right. So since I don't have, well, I'm going to assume that we're working with a full data set here. So we don't need a stack though to export these. So I'm gonna just close this here. And now if we want to export the individual TIFFs here, we can go to File and then Save As and then Image Sequence. Okay, so this is what it's going to name these as. You can check use slice labels as file names. And then want to probably start at 1. And then we have 30,000, so I would use, say, 5 digits. You can put an underscore at the end of this as well, and then it will export them. So actually, let me create a subset of this to show this rather than do all 33,000 of these. So if I do image duplicate, so let's just do. We'll do 1,000 of these. Or 1,001, I should say. 5,000 to 6,000. Okay, and then save as image sequence. Okay, and now we only need 4 digits. Again, you have options here for the file format. Again, TIFF is going to be probably your highest quality, I believe. Click OK. And then we need to find a home for these. So I already had a folder for this actually, that I actually have stuff in. So let me create another one, new folder. DP export to, and then click select. And so you can see we can do this from a virtual stack, okay? And that's what you probably need to do if you had, the full 17 gigabyte data set. Okay, so now as far as verifying that everything exported okay, you can go to File, Open, and this is the folder where we exported everything. So you can see, let's view list. Okay, so you can see right now it actually started. Now we could have started this, since we started with the 5,000th image, we could have started this at 5,000. We didn't have to start it at 1, so we could have started it at 5,000 to note that that's actually where it was within the actual scan data. So it's something to keep in mind. You don't have to start at 1. You can start this at whatever arbitrary number you want. But let's just go ahead. Let's open one of these here. Okay. Yep. And it opens up fine. Everything looks good. And then you can go ahead and you have your sequence of TIFFs, TIFF versions of your seabed patterns, and then you can use those to reconstruct your data. Okay. All right. So that was the quick hitter video, or the somewhat quick hitter video I wanted to do about basic visualization of your data, your MPAD data using ImageJ, as well as exporting of the data as individual TIFFs for later processing. Again, keeping in mind that need to actually, flip the DPs vertically, right? Before you do your reconstruction in your reconstruction software. Again, if the data set was smaller, we could have done that directly. We could have done that with this data set actually, but like with a full data set, unless you have enough RAM to create a stack that large, you won't be able to do that. So just something to keep in mind. It's important, obviously, to have proper orientation of the DPs relative to the image. Okay. All right. With that, I will wish you happy Thursday, and I will see you again in the next video.